Good morning. I'm going to begin talking about astronomy, a little bit of astronomy. I'll begin with what's called the celestial sphere. Humans have been looking at the celestial sphere since time immemorial. Whatever that is, I don't know. But since humans evolved with any kind of curiosity, they look up at the night sky. And when civilization came along, whatever that is, different civilizations had astronomers and made observatories. They're all over the world. Astronomy was important when civilization, if you wanted to find civilization in terms of the ability to farm and sow crops, following the seasons was important. And to do that, astronomy is what you need, okay? So, we'll start looking at the celestial sphere. Today we'll look at coordinates actually, and there are many different systems of coordinates. But let's just do the simple thing. Okay, when I was a kid, I grew up out the country and there was no light pollution. And I knew a lot of stars. I didn't know what they were called, but I knew where to find certain shapes in the sky. Certain shapes, those patterns drawn out by the stars, called constellations, can be very obvious. For example, Cassiopeia is like a W. The Ursa Major has the shape of a chopper's, and you can find the North Star using the two endpoints of Ursa Major, right? You notice I haven't called it the Big Dipper. No, Ursa Major. All right, and then there's a Little Dipper up there near the North Star as well, Polaris. We're very lucky in the Northern Hemisphere that the axis of the Earth points pretty closely to a star called Polaris, right? Not exactly, there's a little bit of a wobble up there, but pretty closely. And from that, you can base your studies. All right. Now, the night sky can be mapped, and there are fixed objects on that map. Fixed objects will be stars and what were called nebulae in the past, galaxies, right? The Andromeda Galaxy is a little wisp you can see out of the corner of your eye if the night sky is clear and you have no light pollution. When my kids were little, when they were babies, what I used to do was bring them for walks on the lawn out in Nantucket and point up and look at the stars. That was the first thing I taught my daughter. I think she's forgotten it now, but it's the first little bit of science she was exposed to. So, if you're an ancient astronomer, your first job is to map out the seasons. And what happens? Well, the sun comes up, and it comes up on the horizon, rises in the east, sets in the west. Suppose you know nothing about the structure of the solar system. All you can see is what the sun is doing, what the moon is doing, and what the stars are doing. Now, the stars rise and set. The stars rise and set. Yeah? The sun rises and sets. Now, I hope to get this right. So, if you're an astronomer, you might mark where the sun comes up on the horizon. Now, in the summer, the sun is going to be coming up, and as you could mark that place where it comes up on the horizon with a rock. If this is your observatory, there's your person. Mark there with a rock. So we'll say that the furthest north, where the sun rises, will be the summer solstice. Okay? And then we have the equinoxes. And there are two. Equinox means equal night. Day and night are of equal length. So there's one in spring, sometimes called the vernal, and there's the autumnal one as well. Now we're going to have another solstice. Here, the day is at its longest, and the night is at its shortest. Here, the night is at its longest, and the day is at its shortest. And here, this is an equinox, the sun comes up, and day and night are of equal length. Now it comes down to explain what's going on here. Well, such explanations were begun in a big way by Copernicus, followed by his student Johannes Kepler. He was German, 1571 to 1630. And Kepler, he lived with all sorts of health problems. And, people don't know about this, but gosh, he had teeth problems and you name it. So he still did great work though. So the autumnal and the vernal equinox are in the middle of the year, and the solstices are on the ends of the year. Okay, so midsummer and midwinter. Now I grew up in Ireland and sometimes in England, and in the middle of the summer it hardly ever got dark at all. In fact, the sky just went kind of green because we're far north. Here we are at 45 degrees north latitude. So the difference between day and night is not so pronounced. If you go really up far north, if you go to Kiruna in the north of Sweden, the sun never sets at all, right? That's what happens inside the Arctic Circle. The sun just goes round on the circle, on the horizon. Now, in the winter, when I grew up, it hardly ever got bright. The sky just went kind of pink. And, people used to get depressed with the long winters. I don't know if it's true or not, but I think there's something to do with the amount of sunlight you get that affects your mental well-being. So that's what your average astronomy begins to do, and a place where you would get this done would be, let's say, Stonehenge, right? Or Newgrange, down the road from me in Ireland. Newgrange is an observatory, and it looks like it was made yesterday. But there's a doorway in it, and there's a passageway, okay? And on the solstices, the sun shines down. Now, in the summer solstice, the sun shines down this deep, deep passage. And it's down a very long, narrow tunnel. And it lights up a bowl. Now, I don't think they got it right. I think the bowl in ancient times was more than lit up. The bowl is kind of slightly concave. That suggests to me that the archaeologists need to go and look at what they're talking about. If you wanted to light up the interior of the chamber way down at the bottom of Newgrange, if you put a bit of water into that, it would reflect the light up onto the ceiling. I think that's what happens. Right now it comes in and it strikes off a white rock, but if you put water in that, then it would really be noticeable. Now, when the sun comes in there in the middle of summer, at midday, in the solstice, well, it doesn't quite hit the bowl at midday. It misses by a couple of minutes. And say, well, that's still pretty good for ancient observers, ancient astronomers to be able to make a situation like that very accurate. But wait a minute, it's even better than that. The reason it misses it by about, let's say, 8 or 10 minutes is because 5,000 years ago, when this place was built, the Earth was in a different position because the Earth has a wobble on its axis. It's called precession. Actually, there are different wobbles. We'll go into the motions of the Earth. They're very, very complicated. Okay, but one wobble, precession, takes about 26,000 years, and 5,000 years ago, that meant that the Earth was pointing, the axis was pointing in a slightly different angle, and that difference of 8 minutes would be accounted for due to that wobble. So, ancient observers, the celestial sphere. So, what is the celestial sphere? Before we begin, we have to look at latitude and longitude on the Earth's surface. Okay, so we'll take it now that Vasco da Gama went around the world, and people know that the Earth is a sphere. It's not a flat Earth. And we have to find positions on that Earth. So we find positions using, as you know, latitude and longitude. Parallels of latitude are fixed. There's one parallel of latitude in the center of the globe, the equator, and there are 2 points of latitude, the north and the south poles. Those points are all fixed. The other ones, the longitude ones, are arbitrary. We have to begin. Where do we begin? On the equator is where we begin our latitude, 0 degrees, let's say. I'll talk about that in a minute. But for longitude, that's arbitrary. We could say begin in Cairo. No, that's not what happens, because rule Britannia, Britannia rules the waves, and so on and so forth. The British had the big navy way back. The first big, huge navy. It was British, and they were maritime experts. And their naval school is in Greenwich, in London. Greenwich Observatory. And you can go to Greenwich Observatory, and there's a copper strip, I think, and you can put your feet on it and stand between the east and the west half of the Earth. And the longitude line goes right through that Greenwich meridian. That's where we begin counting longitude. So let's get rid of this and start talking about latitude and longitude. The free imperial city of Wilderstadt is where Kepler was born. So we take the Earth, okay? Now the Earth is a sphere, and it's spinning on its axis with respect to, well, you have to say with respect to something, with respect to the solar system, okay? If you took away all the stars and the sun and left the Earth in free space, it could never spin. It has to know what it's spinning with respect to. You have to have something to compare its motion to. So we compare its motion to the sun, and with respect to the sun, it's spinning, it's rotating on its axis. Why? Because the rotation of anything defines an axis. So the first thing we do is we put in that axis. Now in the northern hemisphere, very conveniently, there's a star up here which we'll call Polaris, and it's going to be right overhead if you're standing up here. Okay? Now if you walk on, and then of course you're going to have a horizon. Alright. Now you start walking, and you walk all the way down to here. And your hat stays on you looking like this. And a plumb line, if you had a plumb line, would point towards the center of the Earth. And around here, if you cut the Earth into 2 hemispheres, which divide the Earth equally, you will have the equator. It equates the Earth, and it puts it into two parts, right? Now, the first thing we look at is, let's say we're in New York. We can measure this angle and say how far north we are. This angle is about 45 degrees for us. If I call this 0 degrees, it can designate a coordinate to tell us how far we are with respect to going up here. Now if we go all the way up to here, we're going to be at 90 degrees north latitude. 45 degrees here, and 0 degrees here. That's the way latitude works, all right? Now how do we find latitude? Well, first of all, we need a horizon. There's a horizon. When you're standing on the Earth, you just see everything looking around you flat, and that's your horizon. Now when you walk down the street, the moon comes with you because it's so far away. Parallax is minimal, right? It's very difficult to denote any angle. Now, Polaris is so far away that if we walk this distance, the radius of the Earth, about 4,000 kilometers, that's nothing compared to the distance to the North Star, so it will walk with us. And Polaris will be on the horizon. if you're at 0 degrees latitude. So it's not going to have any angle of elevation. If you want to point to Polaris, you're going to point on the horizon. No angle. Let's go to New York. Where's Polaris? It's going to be here, because when you walk, it's going to come with you. And you point to Polaris, it's going to be at an angle. Here's the angle. The angle between your horizon and the North Star is called the angle of elevation of the North Star, will be your latitude. So if you find that angle, you find your latitude. When you walk up to the North Pole and you point to the North Star, you're going to be pointing directly overhead. This here, this angle is a right angle, 90 degrees. So you're going to be at 90 degrees north latitude. You're going to be at 45 degrees north latitude. And you're going to be at 0 degrees latitude. Now you could go down south, in which case you could end up at the South Pole doing the same thing, but your latitude is going to be south. South of what? South of the equator. That's the way latitude works. Now wait a minute, you don't have to be stuck here in New York. You could go at anywhere on the same latitude. New York is pretty far south. I think Cairo is about the same latitude as New York. Athens, maybe, I can't remember. But there are lots of cities all around the world. They don't have to be cities. Places that are 45 degrees north latitude will designate a circle. All right? Let's look at somewhere that's at 40 degrees. No, let's say 35 degrees. That looks at like 35 degrees. Now, all the places around the world 35 degrees north of the equator can be designated to be sitting on a circle going all around the globe. But these two circles are going to be parallel to each other. Yeah? Circles parallel? Yes, you can have that. If you drew a tangent to this circle and a tangent to this circle, both of those tangents would be parallel to each other. So we say parallels of latitude. How do we find them? We find the angle of elevation of the North Star. Let's see how we can do that in practice. Okay, so here's the North Star. Now the North Star can be found by doing the following. You take Ursa Major and imagine its shape. Ursa Major is the Great Bear. But there is a famous Sean O'Casey play. It's called The Plough and the Stars. The Plough and the Stars came from the Irish Republican flag of the time. There was trouble. So, The Plough and the Stars, it was known as the Plough where I was growing up. In America, it's the Big Dipper. But, you know, constellation-wise, Ursa Major, or the Great Bear, is what it's known as. So take the two endpoints and project them, and you will find Polaris. And there's another little one, Ursa Minor. I forget now. Hold on. Ursa Minor has the tail of it touching Polaris. Polaris is the tail of Ursa Minor. But we'll just go Ursa Major finds Polaris for us. So we want to find Polaris. There it is up there. How do we find our latitude? Well, let's split the Earth again. Down here is 0 degrees latitude. Up here is 90 degrees north. And the North Star is overhead. Let's go somewhere up here. To find our latitude, we take our horizon. Remember, Polaris walks with you. Find that angle theta. How do you do that? Very easy. No, I don't have it. The way I used to do it when I was a kid was I'd take a stick, right, and I put a protractor on it. And it's like sighting with a rifle. You look down the stick and you have a plumb line. What does the plumb line do? The plumb line always points towards the center of the Earth. It's a weight. So this is pointing towards the center of the Earth. Now all we have to do is read off the angle. Here's the angle here. Is that the angle? Let me just check. Could be this one. Okay, now I have to double check. So if it's overhead, yeah, 0. It's this angle here. Okay, so 90 degrees and 0, because when you're on the equator, the plumb line is going to be like that. This angle will be 0. So this angle is the latitude. And you have to read it off from your protractor. You can make a thing called a sextant. We'll give you you can make a homemade one, and you can actually, even using an ordinary school protractor, find your latitude quite easily. You walk a half mile down the road and you can detect a difference in the angle just by walking a half mile, a couple of blocks down, believe it or not. Okay, so that's latitude. What about the next one? Well, we want to know where on this circle are we? So we have to start counting degrees. So what I'm going to do is I'm going to draw the Earth again, and this time we're going to look down on the Earth. And say, where is this going? I'm going to convert this latitude and longitude in a while to similar latitudes and longitudes that can pick out the stars for us. And it's going to be the celestial sphere. The celestial sphere is basically inside out latitude and longitude. This time we're going to look down on the Earth. All right? Now, which way is the Earth spinning if we're looking down on it? That's an interesting question. So, we're looking down on the Earth. Let's say this is New York. Here's New York here. Where does the sun rise? It rises in the east and sets in the west. So, let's think. To get the sun to rise in the east, where's the east? Looking down, this is going to be east, and this is going to be California over here. So the sun comes up in the east, means that the Earth has to spin anti-clockwise if you're looking down on it. Go away and check that, right? So the Earth is spinning anti-clockwise, but that's a separate idea. Now we can measure angles anywhere on this circle. We could go all the way around to 360. And 0 degrees again. Or we could just call this, everything this way is going to be, let's see, east. And everything this way is going to be west. Of here, all right? But where is here? We have to begin counting the angles somewhere. That's an arbitrary choice. I told you a minute ago, that arbitrary choice, the one that's said to be 0 degrees, is going to be this one. Well, the great circle that goes through Greenwich, by the way, all the longitude lines are the same length. 2 pi r is going to be the circumference of the Earth. all the latitude lines are different. The equator is the only latitude line that's a great circle. A great circle is a one that, if you made a plane using this circle, and that the edges of the plane were defined by the circle, that plane would pass through the center of the Earth. Great circles. But the only latitude great circle is the equator itself, if you can imagine, because then they all get smaller and eventually the lines of latitude shrink to a point at the poles. But the lines of longitude, they go all the way around the Earth. See? They slice the Earth in half everywhere. So, 0 degrees longitude goes through Greenwich in London. The Royal Observatory at Greenwich is the beginning of counting longitude internationally. And then you can start traveling east. You travel east to 90 degrees east of Greenwich, and then to 180 degrees, the international dateline if you like, halfway around the world. Then you start counting backwards, because this is going to be all going west. 90 degrees west of Greenwich and 180 degrees west. Remember, we're looking down on the Earth. See? So really I shouldn't have written that line this way, because this is the way I have to do my longitude lines. They're all like this. Like pizzas. 45 degrees, 90, what's this? 135 degrees, 180, and so on. All right, so that's longitude and latitude. Now you can find your latitude quite easily with the sextant. To find your longitude, you need to know time, because the Earth is rotating with respect to the fixed stars. There is no star fixed over every line of longitude. But if you know where to begin counting, and you have a clock, you can find your longitude. If you're sailing west from Greenwich, let's say you want to go to America on a ship and you're in the British Navy, you need to know how long you've been sailing for. There are ways to do it. I'll have to look into that. But yeah. Now, years ago there was a quest to find a way to find your longitude, and that quest came out to be like this. The prize was offered by, I don't know, was it the Crown? I can't remember, to anybody who would come up with a device for finding your longitude. Really what they were doing was looking for a way to make a clock. Now they had pendulum clocks, but a pendulum was no use at sea. So somebody invented, I guess it was a spring clock. Now, all the greats started working on this problem. I think Robert Hooke probably worked on this problem because he studied springs a lot. But it went to, as far as I remember, a school teacher, possibly from Wimbledon in London, got the prize. Anyway, that's a long story. Somebody wrote a book about it. I forget, it's a woman. It's called Longitude, and I forget her name, the author. Never mind. So that's latitude and longitude. I didn't get to the celestial sphere yet. We'll leave that for a separate talk. And I will take all this, what we've learned here, and transpose it, because the celestial sphere is going to be an imaginary sphere all around the Earth, with the Earth at its center, and it's going to be the fixed stars on an inside-out background, and they will have their own latitude and longitude because they're fixed.